Hello, in this video we will talk about evaluating pattern accuracy and how we can measure the difference between the 2D pattern and the 3D model. The easiest way to evaluate the accuracy of a model is to simply look at the colors shown in pattern view on either the 2D pattern or the 3D model. The colors shown represent the strain calculated on the mesh, and even though the ExactFlat strain legend is customizable, you can always view the strain legend by going to the ExactFlat options, and once in the options panel we can go to the legend section, and we can change the strain values associated with the different colors, and we get a preview down here. We can change the colors, we can change the strain levels or strain quantities to customize the legend however we want. We can also click the defaults to restore it to the defaults. And the strain legend is a very good way to give you an idea of the quality and accuracy of your pattern. If you have a lot of strain on your pattern, that is an indication that your pattern is smaller than the actual 3D model, and you're going to have to stretch your pattern to get it to fit back onto the 3D model. If you see areas of gray or black, that indicates that we have sag or excess material. So when we apply this to the 3D model, we're probably going to end up with wrinkling or puckering or loose material in that area instead of a tight fit. So the color strain analysis is probably the first way that we get an idea for the quality or the degree of fit for our pattern. Beyond that, there are a couple other ways that we can evaluate the quality of our pattern. The second easiest way is to simply measure the surface area of the pattern piece and compare it to the surface area of the source model. So for this piece up here, we can use the Rhino area command, and this one is telling us that we've got about 88,000 square millimeters. And if we go and compare this to the 3D model, we'll go over to our perspective view here. We'll turn off the model, and that corresponds to this piece here. We can now take the area of the 3D model, and this one is very, very similar. We are only off by about 4 square millimeters. So the 2D pattern has a very, very similar surface area to the 3D model shape, which is another indication that we've got a fairly good pattern here and that the fit is very good. Another way that we can determine the quality of the pattern would be to compare the perimeter length of the different pattern pieces. So for this one, I'll start with the 3D model piece. I will select this back piece here again, and what we're going to do is we're going to use the dupe border command, and this is going to create a polyline representation of the perimeter of this pattern piece, and we'll just drag this off to the side here so it's not directly over top. And now what we're going to do is we can use the Rhino length command to determine the length of that perimeter. So the length of this perimeter is about 1400 millimeters. And now what we're going to do is we're going to go back to our 2D pattern. We'll turn off the model. We'll just stay in perspective view here, and we're going to do the same thing over here. We're going to use the dupe border command to create a duplicate of the border, and now we'll use the length command again to get the length of this 2D pattern border. So the 2D pattern perimeter length is 1,434 millimeters, and the model length was 1,450. So we've got a difference of about 15 millimeters. So 15 millimeters over the entire length of the perimeter isn't bad. So this is a good indicator for the quality of fit. The biggest problem with this one though is we don't sew pattern pieces together considering the entire perimeter. We sew edges together. So a better way to evaluate the quality of fit for this pattern piece, and even when evaluating the edge length, would be to split this perimeter up into individual edge segments. So what we're going to do now is we're going to use the Rhino split command. We're going to turn on point splitting. This is going to allow us to select points on the perimeter, and now we can split this curve up by selecting individual points. So all I'm doing is I'm selecting the division points between seams here. There's one more there, one right here, and one right here. So now, after I press enter to complete the command, I've divided this polyline into multiple segments. So we'll go back to the 3D model, and we will do the same thing to the 3D model curve. So for this one, we've got 3D on the top, 2D on the bottom. We're again going to use the split command. We're going to split at points. We're going to split there, there, and we'll get the corners up here. So now we can start comparing corresponding edges. So this middle one here, if we do Rhino length, the pattern is 221 millimeters, and if we compare the length to the model, we've got 224 millimeters. So the difference between our pattern and model is about 3 millimeters. So even though we have a difference, when we sew these materials together, this model is a car seat. The materials have a bit of stretch, so we're well within acceptable tolerances. 3 millimeters is not a lot, and in fact, when sewing it together, you may have a greater error or less error just because of if the two pieces aren't being sewn together at an even rate, you may introduce error there. Also, we could probably reduce this difference by using some options in the ExactFlat optimizer. So when we go to spring, I'll select the back piece here. I'm only going to optimize one of them. In our pre-spring settings, we can turn on the preserve boundaries option. And we recommend starting with higher tolerances first. So 5 millimeters works very well, and if this is still not good enough, we can always lower this tolerance. We can always rerun the spring command to reduce this difference even more. So we'll click OK, and this is going to help reduce the difference. So we'll notice a reduction in the difference between the global perimeter of the 2D and 3D pieces, as well as per edge differences. So another way to evaluate the quality is as we're optimizing, we can actually see the no seam stretch error. So this is the numerical difference between the 3D perimeter length and the 2D perimeter length. So before we turned on preserve boundaries, the difference was around 15 millimeters. We've already reduced this difference to about 4 millimeters now. So our differences are going to be a lot better. We can also look at average energy density. This is a very good metric to give us or let us know the quality of our pattern. The lower this number is, the lower the strain on the pattern is. So when we've got a very, very high strain pattern, we're going to have a high average energy density. If we have a perfect pattern with zero strain whatsoever, such as a developable surface where we can simply lay the pattern on the model, we're going to have an average energy density of 0 or very, very close to 0. Often we don't see absolute 0 values due to floating point error, precision error, modeling errors, but very, very close to 0 is a very good indicator that you've got a good fitting pattern. So these are all different ways. So we've re-optimized this pattern piece using the preserve boundaries option. So what I'm going to do now is our 3D model hasn't changed, but our 2D pattern has changed. So I'm going to delete this curve. I'm going to once again use the border command to create a perimeter curve. And now I'm just going to go ahead and use the length command. And our global perimeter length is 1,446 millimeters. I'll select all these curves here, and the total length is 1,450. So as the optimization report indicated, our difference here is about 4 millimeters. And we can see this even better when we start splitting this up and evaluating the per edge differences. So again, we'll use the split command. We're going to split at points, and we'll select the different points that we're going to split at. So we're going to pick the 4 corners here, and we'll also choose the inside corners here. So once again, we'll evaluate this middle piece. So the pattern has a length of 224 millimeters, and the 3D model has a length of 224 millimeters. Our difference has been reduced to about half a millimeter. We'll do the bottom. This one has a length of 462 millimeters, and the pattern has a length of 460. So we have a difference of about 2 millimeters. For the bottom here, we don't actually have any piece of fabric that's sewing to it, so this is a good thing that we've got our biggest difference on an edge that is not a seam, because we don't have to worry about a right hand and left hand side being different lengths. So these are just some of the ways we can evaluate the differences between the 3D model and the 2D pattern. We can use the strain analysis that is shown by ExactFlat, and this is represented by the different colors. With the default legend, white indicates 0 strain, cyan is 5% strain, green is 10% strain, yellow is 15%, and red is 20% or more. But the legend is customizable, so it's important that you check your legend to know what the colors represent. We can also evaluate the area of a pattern piece using the Rhino area command, so we can compare the area of the 3D model against the 2D pattern. We can compare perimeter lengths of entire pieces, and to do that we use the dupe border command to create a curved representation of the border. We do that on both the 3D model and the 2D pattern piece, and then we can use the length command to compare the lengths of those borders. And we can also compare per edge lengths by splitting up the curve created by the dupe border command to compare the lengths of model and pattern edges. Thank you very much for watching.